opening to page 22. We'll take our quick look at the calendar. Since the last test, we've spent a couple of days talking about lines. Last class, we talked about some different kinds of equations. We had things that look like they were quadratic, but they weren't really, but they kind of were. We looked at some absolute value equations. We looked at some square root equations. So lots of different kinds of equations we talked about last class. And today we're going to talk about inequalities. And that's something where it's not something like x squared equals 9, but rather x squared is greater than 9. That's an inequality. So we'll do those as well as direct and inverse variation. And just a heads up that our 5th quiz is coming up on March the 9th, which is Friday. Okay? That's our welcome to spring break quiz. Yeah. Any questions on the schedule? Okay. Then on page 22, can we start with Taylor, number 1? Okay, so I think that probably you've had some experience with inequalities before. So can you guys try those 3 with your neighbors? Okay, so what do we do to solve the first inequality? Let's subtract 4 from both sides and we get x is less than 6. Good. 2 steps for part B. What's the first step? Subtract the 2. We get 3x is bigger than or equal to -2. And then divide by 3. We get x is greater than or equal to -2/3. So far, so good. What do we do to solve part C? Divide by -4. We get x is less than -2. Yes? Taylor says we're supposed to flip the inequality. Right. This is the one rule change that we talked about. If you multiply or divide both sides of an inequality by a negative number, you need to change the direction. It's not greater than, sorry, it's not less than, it's now greater than, okay? It's really the only difference between solving linear equations and solving linear inequalities. Any questions on that? Okay, so 2 is our summary. Taylor? Okay, we'll go to Sarah, not quite there. We'll go to Eric for number 3. Okay, so let's try this one. The goal here is to find x. You can see x is right now in the middle. It's trapped. So we want to get it out. Now, you are not allowed to just like add x to everything because, I don't know, it just seems weird because then you'd have like an x in 2 different places, right? So adding x is not a good technique, but we can certainly move the 2 out of the way. How do we do that? Subtract the 2 from, we usually say both sides. Now we'll subtract 2 from 3 sides. So over here we get -5 less than -x less than or equal to 7. And then what do we do to make it not -x but positive x? Yeah, we're going to divide everything by -1. That's how we get rid of a negative. And so let's see, that's a 5, that's an x, that's a -7. How does that look? We do have to flip the signs. So I'm hoping that we recognize that there's a problem with, like, even if you don't remember, you're supposed to flip the signs when you divide by a negative. I'm hoping you can look at that and say, wait a minute, something's fishy here. 5 is less than x, no problem. But somehow that's also less than -7. So somehow 5 is less than -7. Like, it doesn't make sense. So this might be a moment where you can make a mistake and catch it, but I'm hoping we just don't make it. You multiply or divide by a negative, change the direction of all the inequalities. That becomes a greater. That's a greater than or equal to. That's our answer. And then just for practice, can you guys write that thing in interval notation? So we have two numbers, 5 and -7. Which one has to go first? -7. We always write the small one first. And we put a comma. And we put the big one. And the only other thing to know about interval notation is when is it a round parentheses and when is it that square bracket. So at -7, it's greater than or equal to, is that that's the bracket. That's how we say include the number -7. And it says don't include 5 because 5 is strictly bigger than x. That's where we put the round parentheses. Questions on that one? Okay, so when you're ready, we'll move to the next page. And we'll go to 4. I think we're up to Iris. Iris? Number 4.
Solving non-linear inequalities is much harder using their let's solve this x inequality using two practical.
Okay, so the goal is to solve x squared minus 3 is less than 2x. X squared minus 3 is less than 2x. Okay, first of all, this is not the same technique as the other one because there's an x squared. All the ones we just looked at before had x to what power? X to the first. Much different. Okay, so how do we solve it? Well, I mean, you can use we'll use the calculator, but we're going to graph two things. You're going to graph x squared minus 3, and you're going to graph 2x. And so we'll type them both into the calculator now. And once you've got your two things typed in, go ahead and hit zoom 6. The standard window is probably good enough here. Okay, so we're interested in places where x squared minus 3 is less than 2x. I've got this thing, I already took the screenshot and put it in your packet. So x squared minus 3 is this guy, and 2x is this guy in green. And I want x squared minus 3 to be less than 2x. So thinking in terms of y values, this one is the green, and this one over here is the purple. I'm looking for places where the purple is less than the green. In terms of y values, when I say less than, which way are we talking about? I'll take it, thanks. So if we just think about y's for the moment. But if I'm looking for a y value to be less than, that means below, right? The lower y's are underneath, they're below. So really what this is saying, purple less than green, oh, that's where purple is under green, below green. And you can look in the graph and you can see that, for example, if I pick this point out here, purple is way up there, green is way down there. Is that good? No, we want purple to be below green. So that doesn't work. If you pick a point like here, purple is down there, green is up there. Does that one work? Purple is below green in that spot. So that's a winner. And if you pick a point out here, to kind of use our imagination, but green is here and purple, I'm guessing, is up there someplace.
Purple is a parabola. There's the y-axis and below.
Yeah, so we're looking for this distinction. There's some places where purple is above, other places where purple is below. We're looking for all the places where purple is below. And it sure feels like to me that there are a couple of points that are important in this graph, and that's the places where they meet each other. Because if they meet each other, then that would be like solving that equation, right? And it seems like wherever they meet each other, that's going to be the kind of cutoff between the points that work and the points that don't work. So what we need to do is find those points of intersection. Do you guys remember how to do this on the calculator? Where will I find intersect? It's inside of second and then trace, which says calc. And you can see number 5 here says intersect. So we'll hit 5. And then you hit enter 3 times. And it should give us one of those points of intersection. There are 2. So x is -1 and y is -2. That's one of the answers. Okay, so 1 point over here is at -1 and -2. Does anybody have the other point for us? 3 and 6. Thank you. So we use intersect twice. We got to get both points. And now we've got the intersections. And what we're after is places where purple is below green. This is what we want. It's hard to tell the difference between texting and graphing calculator stuff, I see. Okay, purple is below green. Well, it feels like purple is below green for this entire region in here, yes? Those are all the spaces where purple is below green. And this problem, the original problem, had only what letter in it? Only x. So what I'm looking for is only x's. So the x's that I want are the ones that are in between, from there all the way out to there. That's the one x, that's the other x, and I want everything in between. You guys buy that? That's the place where purple is below green. And then we'll come back to that. Sarah, that's a good suggestion. Like in here? Yeah, so this is a good question, right? I mean, clearly we want the stuff that's in between. But actually, like, here's some in between, and all right, technically it's like if the x-axis is outside, but still the, you know, like if I just pick this one point right here, which one is above? There's green, there's purple. Green is above. That's a good thing. So yeah, we actually do want everything from there all the way out to there. And you can imagine maybe taking my whole picture and just leave the axes where they are, but just take that whole picture and pick it up and like put it 10 feet up. It's still the same answer. Like purple is still below green in exactly the same spots. Okay, so what's the answer? Well, it's all the x's that are shaded in here. What's the smallest x? -1. And what's the biggest x? 3. So we're looking for all the x's that are between -1 and 3. And then finally, here's the question. Should it be bigger than or equal to? The answer is no, because? That's it. Should only be less than 2x. If you include these points, you're finding places where it equals 2x, and that's not what I want. So the final answer is just -1 to 3, not including either of those points. Any questions on that? Okay, let's take a look at part B, which is the same exact inequality. We already know what the answer is, but pretend you don't. Same exact inequality, but instead, step 1 is to get one side equal to 0. So how about we bring those 2 x's to the left? Do you guys buy that that's the same, it's equivalent? You flip the inequality when? Multiplying or dividing by a negative. So here it's okay, we just subtracted. All right, and now if we graphed just x squared minus 2x minus 3, you'll get one graph. In fact, let's not use the calculator. I've already got the screenshot here. I think we have everything we need. But this graph right here is just the graph of x squared minus 2x minus 3, a single thing. I want it to be less than 0. What's a better name for 0 in the graph? Where do you see the 0? Michael? not the y-intercept, but the x-intercepts. I'm going to go ahead and, so like if I were to graph y equals 0, just like I graphed y equals x squared minus 2x minus 3, I would really be graphing the x-axis. And just like before, we wanted purple below green, it's the same. You want purple to be below green. And do you guys see that purple is below green for a little tiny space in between 2 points? And Michael had said that it's the x-intercepts that we're after here. So I really want to know what that number is and what that number is, and whatever they are, I'm going to pick everything in between. Now we're not using the calculator for this one, but guess what the left x-intercept is? It's -1, and the right-hand one is 3. You'll get the same answers. We're doing the same problem, just a different way. So either graph two things and intersect them and then kind of think about the picture, or make one side 0 and then find the x-intercepts, which your calculator can do, and then think about the picture. Or if you're really lucky, and usually you aren't, turns out there is an algebraic way that we can solve this problem. It's not what we're after here, and like I said, most of the time it doesn't work, but I just want you to have at least seen it once. So here's how we use factoring. Step 1, get one side to 0. Same idea as before. Step 2 is to factor. Can you guys factor that thing? So how does this one factor? -3 and +1. Okay, I'm going to cheat for a second. It used to be less than, it still is, but we're going to pretend it's equals just for a moment. Because if it's equals, I know how to do it. I can split it up and now it looks normal. So how much is x over here? 3 and -1. You're surprised to see those two numbers? No, of course, it's the same ones the calculator has been giving us. So we got 3 and we got -1. Those are the cutoff points, the intersection points. But how are we supposed to know that we wanted the stuff in between as opposed to the stuff on the outsides? Well, if you have a picture, then it's easy. But if you don't have a picture, you use this thing called a sign chart. And again, it's not the focus of this course. I don't think I'm even going to ask you to do it once, but I do want you to have seen it. So let's make a sign chart. I've got -1 and I've got 3. And what we're going to do is we're going to figure out what the sign of x minus 3 times x plus 1 is for different values of x. For example, let's pick a number bigger than 3. Somebody yell out a number bigger than 3. 4 is fine. If you plug in x equals 4 here and here, what do you get in the first parentheses? You get 1. Second parentheses, 5. 1 times 5 is 5. Actually, don't even care that it's 5. It's called a sign chart. All we care about is the sign. You picked a number that was out here. You ended up with a +5. So we put a little plus sign out there. And the nice thing is that even if you pick a different number, like 7, what do you get in the first parentheses? 4 times 8 is 32. It's different. We got 5 before, but what's still the same? It's still a positive. And so actually for me, I don't pick a number anywhere near 3. I would pick 100. I don't actually care about the calculation. If you plug 100 in, 100 minus 3 is what kind of a number? It's definitely positive. 100 plus 1 is definitely positive. And when I multiply two positives, I get a positive. Doing that means you don't even have to do the arithmetic. You just have to think about it. Let's pick a number in the middle. Somebody want to give me a number in between? 2 is fine. So plug in 2 there and 2 there. I don't care about the numbers, I just care about the signs. 2 minus 3 is what kind of a number? That's negative. 2 plus 1, positive. A negative times a positive is negative. Everywhere in there is a negative. And let's pick a crazy number out at the far left. Negative 100. Negative 100 minus 3 is very negative. Negative 100 plus 1, very negative. Negative times negative, positive. Questions on making the sign chart? If you end up taking a calculus course, you'll do that a bunch. If not, well, this will probably be the only time in your life where you get to make a sign chart. I hope you enjoyed it. Now we just have to get the answer. Remember, from the very beginning, we wanted places where x squared minus 2x minus 3 was less than 0. In other words, where it was negative. Yes? Here it's positive, here it's negative, here it's positive. Where is it negative? In between. So the answer here is all this stuff in between negative 1 and 3. Because that is where the thing was less than 0, negative. Questions on that one? Okay. Number 5 is our next reader. We'll go to Sam.
We now take a tour of proportionality. Ratio is we also stated
Okay. Megan? Okay, so that's our definition for proportional or directly proportional. Just means that one variable is some constant times the other variable. One variable is some constant times the other variable. Okay, we'll look at these examples in just a second, but suppose that I tell you that that you're driving down the highway at 60 miles per hour. Do you guys remember our basic equation that relates distance and yeah, so what's the formula? Yes, distance is rate times time. And what was the 60? What does that represent? Okay, so your distance is 60 times your time. That right there is an example of direct proportionality because one variable is some constant times another. Your distance is always 60 times your time. So if you go for 5 hours, how far did you go? 300, right? If you go for 2 hours, 120. Your distance is always the same multiple times the time. That's an example of two things that vary directly. We'll look at 6, which is a geometrical thing. Eliza? Anybody remember the formula for circumference of a circle? Something with what? Pi squared. We'll put pi there. R squared? No? Okay. I go with the flow. You know, 2 pi. All right. Okay, two formulas that we may have seen before and they're kind of fuzzy up there. So I will just highlight that next week, Wednesday of next week, is a very special day. What is Wednesday? It is Pi Day because Wednesday of next week is March 14. 314. 3.14 is the beginning of Pi. So I know that we're going to miss celebrating this together. I trust you guys are going to celebrate responsibly next Wednesday. But like eat lots of round things, pizzas and cobblers and pies. Yeah. Okay, so what's going on here? It says circumference is directly proportional to the radius. Okay, let's see. So y equals k times x. That's our standard equation for directly proportional. So what's replacing the y? It's the circumference. Okay, what's replacing the k? It's a constant. It's 2 pi. It's okay for it to be two things. It's just a constant. 2 times pi is around 6. Great. And what's replacing the x? Is the radius. So it looks like y equals k times x. C equals 2 pi times r. So that's an example of two things that vary directly. And when things vary directly, you get to say stuff like, if the radius were to triple, the circumference would triple. If the radius got multiplied by 8, the circumference would get multiplied by 8. If you took 3 times as long to make a trip, your distance would be 3 times as long. This is what happens when things vary directly. You can say like really nice statements that that are true. Okay, so for number 7, Eliza, can you read 7? Okay, we'll rewrite our area equation. A is pi times r squared. And I know that direct proportion is supposed to look like y equals k times x. What's behaving like y is the a. What's behaving like the k is just the pi. K is only allowed to be a constant. What's behaving like x? It's r squared. Yeah, it's directly proportional to the square of the radius. It's okay for me to throw something complicated as long as it's a variable, even if it's the square of some variable. R squared is a perfectly legitimate thing. I can treat it like an x. So area varies directly as the radius? No, because if you double the radius, like, do you know what happens? Does the area get twice as big? Yeah, if you double the radius of a circle, it gets a lot bigger than twice as big. Actually ends up being 4 times as big because of the r squared. So yes, we can still say nice things, but you have to say something like, if you double the square of the radius, then you double the area. Like, you have to be consistent with whatever, like, the variable is, whatever x is. Okay, so that's the one definition, directly proportional. We'll go to Serge for 8. Okay, new phrase, very similar equation. Y it varies directly, or y is directly proportional to x means y equals k times x. Inversely proportional, y equals k over x. One of them is k times, one of them is k over. Outside of that, they're the same. Let's go to number 9, Joe. Okay, so you guys know the area of a rectangle, right? What's the area of a rectangle? Length times width. All right, so we know that the area is length times the width, but the area in this case was 100. So 100 is equal to length times width. And I wanted you to tell me that the length and the width were inversely proportional. So let's go ahead and solve for L. How do you solve for L? Divide both sides by W. Solving that equation for L. I'll write it the other way. L is 100 over W compared to y equals k over x. You see it? What's behaving like the y? That's the length. What's the k? 100 in this case. What's the x? It's the width. It's the w. All right. Can you guys fill in the blanks? I'm giving you a bunch of lengths, and I want you to fill in the width for each of those lengths. Check with your neighbors as you do. Okay, so we filled in the table here, and then we got this question. What's true about every length-width pair? 100 with 1, 50 with 2, 25 with 4. What's always the same? They multiply and give you 100. Well, of course they do. I mean, I said the area was 100, so the length times the width must be 100. So it doesn't feel like we're saying anything, but we kind of are making an observation. Anytime you have two things that are inversely proportional, they always multiply together to give you the same thing. No matter what values you pick, they always multiply to give you the same thing. Yeah, and there's nothing special about having one letter or the other. So yeah, the length and width could swap. Okay, we'll go to 10. Ben. Okay, so a kind of boring example. We just want to make sure we can do like a straightforward example before we look at some of the word problems. All right, I'll give you the standard way to do it, but first I'll give you the kind of intuitive way to do it. So if you don't like this way, that's fine. There's the standard way coming up. What did we just say about every pair when you have a inverse proportional? They always multiply to the same thing. Whenever you have inverse proportional, they multiply to the same thing. How much do A and B multiply to here? Multiply 8 times 4 is 32. So no matter what numbers you pick, in this example, they're always going to multiply to 32. So if I tell you that A is 2, what value must B take on to multiply to 32? Must be 16. Like we've just answered the question. They always multiply to the same thing. In this case, it's 32. So 2's partner is 16. Okay, that's the like kind of intuitive way. But if you want the standard way, you just start with the, like y equals, is it k times x or k over x? Yeah, you see inverse, you need to think k over. Well, we don't have x and y in this problem. We have a and b. So we'll just call them a and b. And as Eliza points out, it makes no difference which one is which. In the first example, how much is a? 8. So we've got 8 equals k divided by how much is b? It's 4. So the moment you put in 8, you also put in 4. And then we have to solve for k. How do you solve for k? Multiply by 4. So we get k is equal to 8 times 4, 32. Ah, the same 32 that we had figured out before. So what that means is that this equation now becomes a is always 32 divided by b. And in the second sentence, how much is a? A is 2. So now we get to plug in a equals 2. 2 equals 32 divided by b. And we have to solve that for b. So maybe we'll multiply by b to get it out of the bottom. So we get 2b is 32. And then to solve for b, divide by 2 and get b is 16. You can see why I like the intuitive way. But do whatever's comfortable. Questions on that one? Okay, we'll go to 11, Katrina. Okay, let's pause right there. So the new phrase is jointly proportional. Jointly proportional just means you're going to be multiplying more than one variable. That's all it means. It's just like, is it direct proportionality or is it inverse proportionality? It's all multiplication. Which one is that? That's direct, right? In direct proportionality, it was y equals k times x. Inverse, that's where you get the division. So joint proportional just means direct proportional. You're going to multiply lots of things together. It just means there's more than one variable. So just multiply them all together. K times y times z. Okay, Michael. Okay, so again, lots of letters. Proportional to y. That means times. So the y is going to be times up on top. The only way a variable gets on the bottom is if you see what word? Inverse. The only way the variable gets to the bottom is if you see inverse. You see inverse, whatever follows is going to be downstairs. The square of z, okay, z squared, downstairs. Questions on the vocabulary? Okay, so we're going to jump to 13, and then the rest of the problems for today all have to do with, like, why do we care about direct proportionality and why do we care about inverse proportionality? And it turns out that lots of things out in nature behave either directly proportional or inversely proportional. So let's go to Tyler for 13. Okay, so let's see if we can figure out where all these pieces go. So there's the sentence, and then there's the translated into a formula. That's kind of the new thing for today. All right, so it says directly proportional. Will the thing be on top or on the bottom? Direct puts it on the top, inverse puts it on the bottom. So directly proportional to the product of their masses. Product means what operation? Multiplication. So we're multiplying the masses together and we're putting it where? On top. So right up on top you can see m1 times m2, multiplying two masses together. And the next part, inversely proportional, where will it be? In the bottom, the square of the distance between them. So I've got something to represent how far apart these two things are. I square it. Turns out r is the letter that we're using to represent how far apart the two things are. It's squared. It's on the bottom because inversely proportional. And then in the very beginning it said, where is it? The gravitational force, that's the F, is, and then you can see everything is highlighted except for what? K, and the K is just sitting in the front to be determined. Okay, so what's going on with this formula? Is it just like a lot of crazy words and symbols? Well, why are we not floating off into space at this moment? Gravity. Why is there gravity affecting us? Thank you. I heard the word pull. That's a good word. What is pulling us right now? Yes, and what? Right now, there is one reason that there is gravity affecting us. What is that one reason? If we were floating in space, gravity would not be affecting us, right? You wouldn't be pulled towards anything if you were just floating. Why are we being pulled towards something? It's the Earth. The Earth is sitting here pulling us towards it, right? Now, the fact is, anytime you have two objects, there's always a gravitational attraction between them. Two objects always pull towards each other. So for example, Katrina is pulling Sam, and Sam is pulling Katrina. Why aren't these two people like rolling towards each other as we speak? That sounds good to me. So gravitational force it depends on a lot of things. And one of the things it depends on is how massive the objects are. And so the mass of Sam and the mass of Katrina are insignificant compared to the mass of this enormous sphere that we're on top of right now, right? And so, yeah, there is a gravitational pull between the two of them, but it's insignificant. And they're not going to feel it. They're not going to move. Like nothing will happen because the force of the Earth pulling us towards it is so strong. Now, the fact is, you are also pulling the Earth up. But again, your mass is so insignificant compared to the mass of the Earth could care less. So like you could try to jump up and say, come on, catch me, Earth, but it won't move because you're so light compared to the Earth. So how do you make an attractive force stronger? Well, you can make the objects more massive, like the Earth has a strong attractive pull to us right now. What else can we do? Well, let's see. If suppose that suppose that something happens. We increase, I want to say here, suppose that we make two things further apart. Do you think that the pull they feel towards each other is going to increase or decrease? If we make two things further apart, the pull is going to decrease. You can almost imagine like a magnet that, like you have two magnets that want to go towards each other, but if you pull them apart, eventually like you don't even feel the tug, right? So if you make things further apart, you decrease the force. Well, that's captured in this formula. Suppose that I were to make R equal to, let's say 2. Things are 2 feet apart. So then right here at the bottom, I have some number divided by 2 squared, some number divided by 4. But suppose then that we increase the distance between the objects to 3. Now what's on the bottom? Now it's a 9 because it's always R squared down there. But it's exactly the same numbers on top. I haven't changed anything else. So the force used to be some number divided by 4. Now it's the same number divided by 9. The force has gotten a lot smaller. And that makes sense. As you pull objects apart, the force gets smaller. And so that's kind of captured in this formula. So you can say nice things like if you double the mass of one of the objects, what happens to the force? It doubles. If you double the mass, you double the force. If you triple the mass, you triple the force. Things are a little bit more complicated on the bottom because it's a squared. But suffice it to say, if things get further apart, the force decreases, and that's captured in the formula. Okay, we'll go to 14. Who's our reader now? I think we're up to, is it Tyler? No, Tyler went already. Sarah? 14. Okay, so let's see if we can get our hands on this problem here. Anybody know anything about like aerodynamics and why do planes fly? Michael? Pressure is a good word. Is a good word. Okay, so what makes a plane fly? It's not the engine. It has to do with the wings. Why do the planes have these enormous wings off, like outstretched? And why do birds have these enormous wings? I mean, like, you could look at a bird and say, well, it's got small wings, but relative to the size of its body, bird's wings are really, really, really big. And so it has to do with pressure and it has to do with lift. And so I think I know maybe even less about this than Michael does, but I'll try to share what I know. And if any of it makes sense, then super. You've got, imagine a wing sitting out, like stretching out from the plane. Air flows underneath the wing and air flows on top of the wing, right? The wing is not just a perfectly flat thing. The wing is curved along the top. It's flat on the bottom, but the wing of an airplane is curved on the top. So as this air flows above and below, some of the air needs to speed up because the air, which air has further to go to get past this wing? It's the one on the top because of that curve. So the air on the top has to go a little bit faster to make it to kind of catch back up to the air on the bottom. And this is where I really lose it. It has to do with pressure, but it turns out that the pressure on the top is going to be less than the pressure on the bottom. And so there's somehow this force going up, trying to push the wing of the plane up because there's this pressure differential. In some sense, the stuff on the top is lighter. And so it's more buoyant, yeah, like kind of gets pushed up. This force that's now pushing up, it's very counterintuitive because we're so used to every force pushing down. The only force that we really have experience with is the force of gravity. But if you get enough of this force going up, then you can lift something that weighs many, many tons, like an airplane. Enough force to counteract the force of gravity pulling down. And so there are some different ways, it turns out, to make the force going up stronger. And we're going to kind of figure out what those different ways are in this problem. So can you guys work in at your tables with this? Start off with trying to get some equation and then solve the problem. Okay, so let's come on back together. I think most of the groups have made real good progress on this one. So first we need to come up with our equation. This L is equal to K times S squared times A. So you get that from the sentences. And then you plug in all the known stuff from the first sentence with numbers. Eliza? Good question. Varies and proportional are the same. Yeah, they're synonyms. So we plug in the known numbers and we do whatever we can to find K. And in this case, K is a really small number, 0.00136. And then once you know the value of K, you can plug it back into the equation again. But now you get to plug in the numbers in the second sentence. So that's where the 40 and the 600 come from. Anybody have this number for me? Six. Yes. So yeah, it's really common that like we'll give you one sentence with all the numbers in it. That allows you to find the constant. Then we'll give you another sentence with all the numbers except for one. But because you already have the constant, you can then use the equation again and find that one unknown. Yeah, you really got to separate it in your mind. It's like two different pieces of information. Yeah. Joe. Let's see. Will K be stated in words? I think let's go ahead and figure out what the units of K are, and then see if that has any meaning for us. So K, let's see. So S squared, and then times A. Okay, so let's fill in some units here. What were the units of the lift? That was in pounds. What were the units for S? Was in miles per hour. Notice the parentheses there. The miles per hour are getting squared. And then the units for A was square feet. Okay, so let's see if we can clean this up a bit. K times, we've got miles squared per hours squared times feet squared. Boy, I suppose we could clean up the feet and the miles by doing some conversion type thing. But if I divide everything, if I want to get K by itself, then all this stuff comes over here. And let's see, we're going to get a pounds. We're going to get an hours squared divided by miles squared and feet squared. Those right there are the units for K. Yeah, now you see maybe why it's not included. Yeah, it's pretty common for like complex stuff like this for the units of K to just like be crazy. The same kind of thing is true for that this formula that Tyler read for us, the laws about gravitational force. Like K has units on it, but they're so messy that like we hardly ever write them. Good question. Okay, so here's what you're supposed to take away from that problem, besides the being able to do the math part of it. It turns out there are two different ways to help you get some more lift, more force that allows you to fly through the air. There's speed and there's area. If you make the area bigger, what happens to the lift? Goes up. If you double the area, you double the lift. Super. The difficulty is that making a wing, like the wings are already quite large. Why are they so large? Because they've tried to double the area a bunch of times to double the lift as much as possible. So in theory, if I had wings on me that were big enough, I could walk very slowly, and eventually what would happen? I would fly, but I would have to have these enormous wings in order to get enough lift to do that. So what's the other side of things? What's the other way to make it so you get more lift? Is your speed. So why do you go like 100 miles an hour on the runway? Because you need to get your speed up high enough to get enough lift to overcome gravity. And in fact, if you had a choice to either double your area or double your speed, which one would have more of an impact on your lift? It's the speed, because the speed is being squared. If you double the area, we'll get practice with this in the very next problem, but if you double the area